is the Atmospheric Data Community Toolkit. And it's really a Python toolkit for data exploration and analysis of atmospheric time series data sets. So more on like the research focused side of atmospheric science. It's built off of the X-array object. So everything in ACT uses the X-array object as its base. Also it pulls in pandas, NumPy, SciPy, Matplotlib. And we also have optional dependencies that we pull in, like MetPy here that you just saw, and PyArt and others where appropriate. We definitely don't want to be duplicating effort and code if it's already out there. So, the MetPy sounding that was just shown. We've written a wrapper around that for the ACT or for the ARM data to plot out skew-Ts, and there is an example in the tutorial here that I'll show you. So again, trying to use what's already out there. We do have modules for many different aspects of the scientific life cycle in ACT. So there is a discovery area for calls to download data. Now, as you saw with Siphon, there is already some stuff out there. So we haven't really advanced this part much because we want to be careful and actually have time to look through what's already out there. Because again, we don't want to duplicate effort here. We have an I/O module for reading data of various formats into that X-array data set, from NetCDF, CSV, text files. Even we pull in an optional dependency to read in raw MPL files as well, micropulse LiDAR. So there's a quality control module where you can apply different tests and filter data out. And I'll show more of that in our tutorial here this morning, or this afternoon, I should say. There's a corrections module for applying different corrections. A lot of it is LiDAR related right now. Visualizations, these are built on Matplotlib, but there is interest in expanding this out to more interactive plots as well. And then retrievals, and this is an area we really want to kind of advance forward a little bit here. These are just advanced calculations that we've started building up. Anything from calculating the infrared sky temperature from the ARI data to sea surface temperature from our infrared thermometers, and more. I have some examples in the tutorial here as well. But our goals here really, with the instrumentation that ARM deploys, it's anything and everything, from soil measurements to surface meteorology to LiDARs, radars, scanning radars, aerosol systems, etc. A lot of this stuff is used in a lot of other groups, from Ameriflux, for NEON, NOAA, NASA, universities, international institutions, and really just a general research community that uses the data from these groups as well. There's a lot of overlap there in what they do to process the data, visualize it, and work with it. So one of our other goals here is to just reduce that duplication of effort across all these different groups and have a standard code base that they can go to when working with time series data sets from these instruments. It also creates transparency, having this code out there. As we've heard the last few days, it is one of the pillars of being open source, open science. It gets it out there. It has more eyes on it. You can catch more bugs having 10 different eyes on one piece of code than 10 different siloed efforts going on and pieces of code. So, and it also allows us for the flexibility. So, with this code, users can take it and modify it and use it how they want. So if they want to apply different limits or have different thresholds for things, they can go and do that as well. Now, I'll talk about some of these here in a little bit, but it's important to note that ACT is installable through pip and Conda using act-atmos. And I should note we just actually had a release last night, so we're up to 1.1.6 now. And thanks to Ken Kehoe here for staying up late and debugging and fixing some code with me last night. So the actual ACT repo is under the ARM DOE GitHub organization. So you can find that there right alongside PyArt, which is going to have a tutorial tomorrow. So as I mentioned earlier with RadTrack, one of our core practices here with ACT as well is we really want to funnel the citations, to the papers behind the algorithms. So as I mentioned earlier as well, we're following the same practice. We have a reference section in our documentation that points to the papers, technical reports, or whatever that the code is based on. And here this example just shows the reference for our sea surface temperature measurements, I believe, calculated from the IRT that we pulled in. Now, we try and do this for everything we know of, so getting it in there, is one of our core practices. One of the others is that we don't necessarily have a paper, a static paper for people to cite on ACT itself. So all of our contributors get added to the author list on the DOI. The citation is auto-generated with each new release using Zenodo right now. So you can see on the right here all the people that have contributed to it so far. This is up through 1.1.3 release, but we really want to just give everyone credit for what they've done with this project and this library. So the other thing, I was looking at MetPy, I was a little jealous. You have 95% coverage. We actually spent a lot of effort last year bringing our coverage up from about 70% to 90%. And that's really, we want to stay above 90% with this as we go forward. And this is just, every time that someone requests to add code in, or that, we create a new release, we run these tests on the data to ensure that, whatever change or on the code, so that we ensure that whatever changed in the code doesn't break the existing function. So it's essentially passing a known input and looking for that expected output with these unit tests. And that's, showing that 90% of our code actually is covered by these tests. A lot of that 10% is really hard to get at because it covers a lot of fringe cases that are error checking and whatnot that we don't generally see a whole lot. So now we just developed our second roadmap for ACT. This is kind of looking at what our priorities are over the upcoming years here. This was based off of a survey we handed out or passed around last year. And looking forward here with ARM having a new aircraft coming online in the next couple of years, with the UAS activity coming back online in the next couple of years as well, we saw that the aircraft or UAS related functionality was really a high priority to get stuff in here. We also saw that during the Ameriflux meeting, there was a lot of questions and requests for plotting, for visualizations, analysis, QC for aircraft or UAS related data. So that made it up onto our list as high. As I mentioned earlier, the retrievals were also high. We definitely want to add more here. It's a good way to just double check and verify some of the existing retrievals that ARM has in VAPs, but also to expand the transparency and really the flexibility for our users to kind of take and modify as well. In the past, we've actually had some Windows compatibility issues, but we are testing on Windows now as part of our unit tests, and we'll continue to work at that. Some others here, ARM Data Surveyor. So the ADC quick looks that you see in data discovery are actually generated using this wrapper called ARM Data Surveyor that is really built around ACT. It's just a command line module, and we just need to make sure that's continued to be maintained and supported. Additionally, we're going to look at performance improvements here to speed up the loading, reduce the package size, and really just optimize things a whole lot more going forward. We are using Dask in a number of our scripts to speed things up, but more is generally needed. And then some other areas here, I won't necessarily spend too much time here, but just more education outreach, more tutorials, examples. Looking at the discovery module to see where we can pull data from or reuse code from other sources to pull that data. And then visualizations, like I mentioned earlier, interactive and 3D plotting here. So with that, I will bring over a new screen here. So this is the ACT. I'll put a link in the chat, the ACT repo on GitHub. And I won't spend too much time here, but just so you're aware, there is the documentation linked up here as well, which Max just recently revamped in this new theme, which looks pretty nice. So we have our user guide, API reference manual, where you can look through all these different modules and see what's all in there. And then we have a nice example gallery as well that we're always trying to add to with a number of different examples. So please go check that out. But for now, let's dive into this tutorial session. So I'll put this link. I'm going to start, back in this book, this Jupyter book. For ACT Basics here under day 3. Now let's load it up on Jupyter Hub under that rocket ship. So it should pull up there. I'll give it a second here for you all to bring that up. But I guess while you're doing that, what we're going to cover today in this tutorial is looking at some of the basic features of ACT around quality control. So, in ARM, there's a lot of different ways to get quality control information for your data. In many of the files that you might receive when you download it from Data Discovery or through the web interface or web service, there's going to be embedded QC variables that have information about quality control. But there's also information available in what we call data quality reports. And those can be accessed through a web service as well. And we're going to show you how to kind of work with both of those today. Now, ACT should be installed on here, so we can generally skip this. But again, if you want to install ACT on your own machine, you can pip install it with act-atmos or through Conda, doing the -c Conda Forge act-atmos. Now, as we scroll down here, we can see some of the imports. Really, it's going to stay pretty simple here. We're going to import ACT and matplotlib, and that's really just to show the plots here as we go. So once that's in, we're going to check our version. Now, as I said earlier, we fixed some bugs last night quick. So it should be at 1.1.6 here. And now if you're not seeing that, please do follow Max's instructions earlier that had you go to the hub control panel, stop your server, and then restart again. And that should clear that and get the latest ACT version loaded up. But if you're seeing that, let's move on to downloading some ARM data using the ARM Live data service. So if we click here on that link, this will take you to the web page where you can log in for the ARM Live data web service. And what will happen will be that it'll give you a token. But in the interest of simplicity here, we actually already have a username set up, ARM Live training, and a token that's just valid for essentially this week during this training session. So we're going to use that. And there's a function in ACT already to interface and connect with that web service. So we're going to call that function here, which is just discovery.download data, and we'll pass it the username and token. And for this example, we're going to use one of ARM's instruments called the 7-channel multi-filter rotating shadow band radiometer, which I hope I got that right. But this is just one of our radiation instruments. It has 7 narrowband channels that it measures radiation in. And we're going to grab that data for 1 day, essentially. So from March 29th, 2021. Now it's going to store it's going to download the data and store, the file paths in this result. So if we run it, it's pretty quick here. It'll download the data. We can see where it's located here. Now we can just take that results variable, and we're going to use ACT here to read it in. So we can use this act.io.armfiles.readNetCDF, pass it, the list of files. If we had more than one files, it's the same call. It'll read that in. And then as was mentioned, I think by Ken, is that Xarray plays very nice with Jupyter here, and so we can kind of print out that object in a nice, somewhat concise manner. You can see the dimensions, the coordinates, our time, and there's a bench angle coordinate as well. And please, someone do stop me if there are questions that I should stop and address in the chat. Yeah.
So I think Sudant is asking if ACT can be used to download data from IOP, which I answered it. But,
okay. Yeah, we don't have that capability, so at the moment. Thanks, Gary. So if we look at some of these variables, there's definitely a lot in here. So just looking at the first one here, we read in the ARM data set. We can see all the different attributes that come with it. So like the valid min, valid max, and then the corresponding quality control variable here is QC underscore hemispheric underscore narrowband underscore filter 1. And that's just the ancillary variable that holds the quality control information. Now, in many of ARM's data sets, that QC variable is actually in a format of like a bit-packed QC. And I'm not going to get into bit-packed QC a whole lot. There's some great information on the DQ office's website, dq.arm.gov, that talks about that. But essentially, you can trip or flag multiple different tests at the same time in essentially one value. So we'll look at that here in a little bit. But before we actually do, just looking at this QC variable here, I'll close that one so it's a little bit easier. You can see it says see global attributes for individual bit descriptions. So essentially, this is saying that there's some generic tests that are being run. We can go look at the attributes here to see what they are. And if we scroll down, we'll see these QC bit descriptions, so what the test is essentially, and the assessment. So in ARM, we define these assessments to be missing, bad, indeterminate, essentially. And what we can do here now, one of the things is that the QC and this information here that's read in, that's from the ACT or from the ARM files, it's not quite CF standards. And in order to use the QC modules, the QC functions in ACT and kind of keep things consistent, we have to clean up the ARM files to this CF standards or climate and forecast standards. And there's a function in ACT to do this. Ken did a great job writing this. He just recently added this, as a call to that readNetCDF. So we could do like cleanup QC equals true, and it would clean up that QC to CF format for us. But for this purpose, let's just run it right here, and it should go through, clean up the data. We'll look at the same variables that we looked at earlier. So this first one, the hemispheric narrowband irradiance filter number 1. You see it looks a little bit different. Some of the information has been removed, like the valid min, valid max. But if we look at this QC hemispheric, the QC variable has that information in it. It changed it from valid min, valid max to fail min, fail max to follow the standards. And it also pulled that quality control information out of the global attributes and added it in here as well. So once we have that information, let's actually go ahead and plot up this data. So I'm just going to set this variable. I'm going to look at filter number 4, and I'll tell you why I picked number 4 here a little bit later on. But we're going to open up a display object in ACT using this time series display. We're going to pass the data object to it, specify a figure size and a shape. So we're going to have 2 rows, and this will just be in 1 column essentially, since we didn't specify a number there. So we're going to use this display, and similar to like MetPy and Matplotlib or Xarray even, you just call this display.plot, pass it the variable and where in that plot you want it, and then the nice thing with ACT is that we also have some features available to plot up, say, like the day-night background. So it'll look for the latitude and longitude in the data file or in that data object and calculate sunrise, sunset, and then a solar noon and plot that out accordingly. And I'll show you here in a second. And then we're going to plot up the QC using this QC flag block plot function here, passing again the variable and the index, which will be the second plot essentially, which in Python you start your indexing at 0 there. So if we run that, we can see what our data looks like and the corresponding QC that was in that QC variable. So we can see there are some spikes in here, so we don't necessarily see that nice solar curve we would expect to see with some of the solar radiation data. And in the QC down here, you can see there's 3 tests being applied. So which is kind of what we saw earlier. The value is equal to missing value. Value is less than the fail min, which in this case I believe was 0. And that somewhat does happen overnight with this instrument, because it's just so close to 0 that the noise will fluctuate and bring the values below 0. And then value is greater than the fail max, and we can see a couple points are getting flagged here. So let's see what happens when we remove that data. So if we essentially take our object, we have some methods there to filter the data in certain variables here. So if we call it object or obj.qcfilter.datafilter, pass it that variable we defined earlier, and then looking here at the tests, we want to remove, let's just say we remove 2 and 3, and as of right now, we want to keep the QC instead of getting rid of it, the QC variable that is. So we'll just keep that QC, and then we'll replot this. And now you can see some of the data here where the fail min was passing, got flagged out and removed. And then some of the data here where our spikes were removed as well. So we can see a little bit more of the curve, but it's still not a great view of the data. So let's look at the DQRs. So these data quality reports, they're submitted by a lot of them by the ARM mentors or the translators or our ingest developers, but they're ways of communicating additional quality control information out to our users. A lot of times when people order data, they're going to get these DQR reports as part of their data order. They're visible in data discovery as well on that timeline that Maggie was showing yesterday. And they're machine readable, which is the best thing. So there's a web service we can access these. And we have a function in ACT here to call that web service. So essentially we're going to pass it the object. That object is going to have the data stream name in. We're going to pass what variable we want. And this will pretty much go grab that DQR and put the information into the QC variable. So if we plot that all up again, we can see the DQR is here for a shadow band misalignment. So there's something going on with this instrument during this period. Now, we could just clear all that out and delete all that, but for this case, I kind of want to look into that a little bit more. Now, with that DQR, with the web service, there's a lot more information you can get, but you can also go and look at these DQRs using through data discovery, essentially, and find, for this period, there's a lot of reoccurring times where this problem occurred, which happens with these misalignments. So, but that's just another way to look at those reports. Now, so we have this area misalignment. I still want to get a better look at the data. So let's apply a new test to maybe filter out some of those spikes. So what we're going to do here is kind of using that same QC filter method, we're now going to add a greater than test. Passing the same variable, we're going to give it a max of 0.4, and just as the test meaning or the name we're going to give it, we're just going to say a new maximum test limit. And then we're going to filter the data out from that test. So you can see we were up to test 4 got added with the DQR when we added that in. Now this would be test 5. So just kind of streamlining here, let's run that and see. And now you can see, you know, we filtered out some of those spikes, and we can get a lot better or a lot clearer picture of the data. And you can see where this DQR lines up, the data actually gets pretty noisy. Now there's likely some clouds in here as well, but this is a clear signature of the shadow band misalignment in this instrument. So we can kind of filter and play around with the data as we go through to really, you know, engage with it. Now, also in ACT, there's a lot of different things in ACT. I'm just focusing on the QC now because that seems like that's a big importance to a lot of the data users of how to interact with ARM's quality control information. Now, there are some specific quality control tests for these instruments as well. So in this case, we have what's called a fast Fourier transform test that was adapted from Alexandrov et al. 2007. Now the link here will bring you to the documentation for this. So you can see what all the options are, what the presets are, so you can change these as you wish. And this is just a good example here again of the references that we are trying to get in here, so it's nice and easy for you to grab and cite if you do use these. So now we have this test, and it should be able to actually pick out the shadow band misalignment as well. I'm not going to get into the details of that. Our mentors are the experts on what exactly is going on with the filter band here, or the shadow band when it misaligns. But there's a way to use this fast Fourier transform to pull out when this is having issues. So let's run that, and it'll automatically get added to the QC here. So we're going to run it and display it. And the FFT, the fast Fourier transform method, I do believe that one does use DASC. It does take a little bit of time because it's like I said, it's an adaptation, so it's essentially a moving window that it tries to do this FFT on in order to get, you know, accurate start and end times. So you can kind of see it does line up fairly well with what the mentor had provided in the data quality report. Now, you know, in the areas where there's maybe some clouds or some reflections, you don't quite pick it up, but you know, it does, you know, somewhat match up with the start and end times here a little bit. Now, there's ways you can adjust those thresholds, like I was saying or showing there, and you can play around with that and those thresholds to get, you know, either more sensitivity, less sensitivity. You know, definitely, you know, in ARM we don't want to overflag things, so we kind of err on the side of caution, I guess, with some of these tests. But that doesn't mean that, you know, you can't go in and play around with it. So, you know, with that, once you have all this QC added in, you don't just lose it, essentially. You can use the built-in X-ray functionality, which is nice as well. So with this object, it's an X-array data set. So we can just do to netcdf, a file name, and it would print it out and save it to a netcdf file. And it would essentially look like, you know, here, let me just show it. Like an ARM file, but with all of this, you know, cleaned up information in it. So we can, you know, somewhat take this, clean it up, add QC, do what we want, and then you can save it back so that you only have to do it once as you're kind of exploring this data. Now, with that, I did mention that, you know, since we're built on the X-array data set, One thing here that I'll maybe just show you here is that you can still use like some of the X-array functionality as well. So, for example, here you can still use some of the plotting functions. So we'll just kind of do obj of the variable we've been using and plot that out. So that's also a quick way that you can plot this stuff out. Of course, we've already applied all the QC, so it looks nice here. But you can use that for quick looks here as well. The goal is just with the visualizations in ACT, we hopefully are adding more value on top of what could be done with these plot functions already in X-array. So now that was the first part here with the QC. So I'm going to just pause a minute and see if there's any questions on the QC portion. So that's a good question. So when we use ACT to download large amounts of data, can it control which files are already in disk and which ones we need to download? No, actually at the moment it cannot. So I guess what I've always done is I have somewhat of some generic code I always put into all my scripts that'll, it'll look in the data stream or the directory where data was put normally. And if data are there, it won't download it. But otherwise, the function is set up to essentially download all the files in that period. But that would be a good feature request if you're willing to add in an issue on the ACT GitHub repository. So can you also show the solar azimuth and our elevation angle in the background? So with this day-night background, essentially we could plot it up if we have that information. I do believe we have in this object, I want to say there was a solar angle, but we don't quite have that built into the day-night background at the moment. That's definitely a good idea, though. So, no, I guess we don't have it in the file, but essentially with calculating the day-night backgrounds, we should have that information available. So it probably wouldn't take too much to get that sort of feature to add in the solar elevation angle or azimuth angle as well. Again, if feel free to add an issue request. To our GitHub page, and I'll actually.
Adam, one quick question. Actually, I'm going to answer it while you're looking into that. Is that okay?
Yeah, go ahead.
Yeah, so there's a question about whether ACT can download large amount of data, and if the data is already downloaded on the local system, whether it knows and not duplicate or try to do it again. So right now, I don't think that would be the case, but in the future, we will look into additional way of supporting data downloads. For example, ADC supports downloads using Globus Online, which allows you to exactly do what you're asking for in terms of managing the download. So that's something that we can do in the future.
Yep. And I think that kind of goes along the lines of the other question there on, if files are updated on the ARM server, can ACT know if the local file is up to date with those on the server? So essentially, maybe we have a reprocessing request, fix the data, or reprocess it using a newer ingest. Can it know if the files are up to date? That's definitely not something that's there now, but it's something that we can look into.
Yeah, so Adam, that's something that we recently implemented within the data discovery. So users can go back to the previous order and see if there are any new files available. But other thing we could do is potentially extend the support of threads, as Drew mentioned in his talk, right? So discovery provides threads as part of the data ordering or data download. So if ACT can, if we extend the ACT to support the threads, that would definitely help with that.
Yeah, no, I agree. I think there's more we can do in that area. So,
Yeah.
and then from Fan, can ACT compare the LiDAR data with other data, such as wind data from the TBS? Now, if you're talking about actual quantitative comparisons, we don't have anything in there at the moment. But of course, you can always plot up those sorts of wind barbs together. I'm guessing you're maybe talking about the Doppler LiDAR and the TBS, and I do believe the DQ office is already doing something like that. And we actually have an example down here in this next section that I can dive into here in a little bit if we can get there in time. So maybe I'll go into that. You know, I had some more examples coded up here of some of the different things in ACT. In order to kind of dive into these examples, though, we just need to import NumPy. So again, the standard import NumPy as NP. And the first example here, we're actually just going to download a month's worth of data from the SGP surface meteorology instrument at the central facility. So this is for May of 2021. So again, essentially I'm using my same username, token, just really changing the data stream and the date. And that's what's really nice about the ARM Live web service. It's just so easy to use to download the data. So we're going to read that all into an object and pass it to this windrows display. We're going to say that, you know, we want the direction. These are the direction and wind speed variables we want to plot up. And then we're going to give it some speed bins. So using this NumPy linspace, we can define our bins. You know, essentially we want 5 bins in between 0 and 10. And then we're going to put up a legend and show that plot. So doing all that, you see it downloads all the files, and then it just pulls it in and creates the nice windrows there. So that's one of the options in ACT as well. Now with this, with many of our surface meteorology systems that are located at a central facility, we have what's called a present weather detector as part of them. And you know, with these detectors, they actually record what the present weather is like in the WMO codes. But you know, of course, those can be easily decoded. We've put in a function to ACT as a utility to decode those based off of the 4680 table from WMO. So we can take, you know, let's just take one of the files here. So we're going to take the index of the 21 here, so the 22nd file, and we're going to pass that to decode the present weather. And then I just want to plot out and list essentially where that code was greater than 0. So actually where it's reporting something other than clear, and just kind of show some of that. So you can see here, it does go through, it uses the data that was in that present weather PWD, PW code instantaneous. So we see rain, not freezing, slight. So these are all the codes that we already have coded up, so you can use that to really decode those. And then going to the wind retrievals here. So Ken's done a great job of coding up this retrieval to get wind profiles from the Doppler LiDAR PPI scans based off of our mentor, Rob Newsom's paper from 2016. So, you know, for this example, we're going to use some test data that already exists in ACT. So in our test area where we run all of our tests, we have a lot of that, you know, the known input essentially. So we have those sample files that we're going to read in. We're going to compute winds from this PPI object, and I set a really low threshold here so you can we can play around with that a little bit to see what happens. And then we're going to want to plot up a time series of this data using that same time series display. But instead of just plot, we're going to plot barbs from speed and direction. So then we give it the direction and the wind speed variables. And we're just going to say don't invert the y-axis here. So it uses height. And it should process through, I do believe there's 2 files it'll process here. Now this one never took this long before in my testing, so hopefully, there we go. So as you can see, it took in 2 files, it got the profiles here, plotted up. Now you could also add, the one thing I didn't show in this example is that you could bring in other objects. So you could read in another data set from the TBS, say, and add it when you're creating this time series. We could essentially pass it a dictionary of objects. So say we wanted to do that, and then for the Doppler LiDAR, we have that wind object, and then for the TBS, let's just say we had a TBS object. That's how we could pass this in and be able to plot up data from multiple different instruments on the same plot. So in this instance, we would just do another one of these display plot barbs from speed dir. We would have to specify which one we're wanting to plot from. So in this case, we would just do like ds name equals dl to match up with what we have in our dictionary up here. But there's ways of doing that. So and of course, with what we get from matplotlib, again, it's all built on matplotlib. We can take those axes from the plot and apply some of the matplotlib features or functions as well, like setting the x limits, setting the y limits, and so forth. So that's one area that is nice to be able to reuse. So and just taking a minute here, it looks like Ken answers the question. Yeah, so it looks like, yeah, we do have the function to calculate that azimuth elevation, and we could plot it out essentially. We just put it on the second y-axis. So, okay, so we saw from Drew and Ryan on MetPy how to kind of build up a skew-T. Now, we have a function in ACT that's built around the MetPy skew-T two functions to actually just make it nice and easy for plotting up just a standard skew-T diagram. So here we're going to import MetPy. We're going to read in test example radiosonde file. And then we're going to set up that skew-T display that we can then plot the data. So we're going to plot the winds on here as well. That's just kind of the standard we did for this this function. So we do the U wind, V wind, then we give it pressure, temperature, and dew point, and it'll take that and essentially do what it needs to do to get it into MetPy and use the MetPy function. So adding the units as well that Drew was showing. So in plotting that out, we get this skew-T diagram. You have your wind barbs on the right, which was one of the homework questions I guess Drew had. So sorry if I'm helping them cheat here, but it can show you just this nice simple skew-T then. I do definitely want to look more at MetPy because it would be great to get that hodograph as well going on these. For now, we have a function in ACT to just plot up a separate geographic plot display. So whether it's a radiosonde or aircraft data or a ship, we can plot up the data using the lat long in the file. So there's this geographic plot display as part of the plotting library. So we're going to take that radiosonde object and data that we read in, that data set, and we're going to display it. We're going to display a data field, the pressure essentially. So we're going to color code the path based off of the pressure. And we'll give it a title here as well. Now, that should print it out on a nice kind of Cartopy map here with the pressure noted here in the color bar as well, and it's shaded in. So we have that capability there as well, which is just nice to see the spatial context of this information. Now, one of the things that we also have, one of the retrievals that was newly added is calculating the PBL height from a radiosonde based off of the, the Liu-Liang method. So, for this, and this is maybe where we need to look at, how MetPy is doing it with units to make sure, we have it all correctly. But for this, we need to have the units in degrees Celsius. So we have a utility in ACT to actually change the units for your variable just with this essentially method call here. So we're going to change the temperature dry, the T dry variable here 2 degrees Celsius. We're going to pass it into this retrieval to calculate the PBL height. And we're going to just print it out here. So the regime is NRL, and it's given a PBL height of 950. Now, with this method, there are, and I'll bring it up here on my screen. If I can find it, right there. So there are some presets in here, essentially. If the pressure isn't essentially decreasing monotomically, we'll smooth out the data a little bit. There's also options whether it's over land or water, and then we also have some options to set thresholds for the low-level jet as well. So this is just one of the ways we're trying to be flexible with these algorithms and provide you the ability to update these as you'd wish. We also just note that there are some differences here with the implementation in the ARMBAP, and really just try to describe that. So we're really open and transparent with how this is being calculated. So, and then the last thing I have here, I'm not sure how much of an interest this would be, but essentially there's a way that we can mimic the ARM data files. So, we can create an object from what's called a data object definition, or a DOE. So, ARM, essentially in all of our ingest processes, they create these DOEs, which essentially is a lot of the header information you see in the netcdf files. It's a way to streamline and standardize variable names, the attributes, all that. And we essentially can create an empty object from that. So if there's a researcher out there that has similar instrumentation like a surface meteorology system, and they wanted to provide a PI product to ARM, they could essentially make it look exactly like an ARM netcdf file. And I guess in my mind that kind of increases the usability of it. If it looks the same, has the same variable names, it'll be a lot easier to use if you're already using surface meteorology data for something. So we can call that, and this will take a little bit because there's a lot of different versions of the Met DOD. But we can call that, and it'll create an object, X-array data set, essentially, with 1,440 samples. So essentially, like with a 1 minute average type of sampling rate in the time dimension. Now, this part here, it's not quite necessary, but it's scalar fill dim. So a lot of times our lat long altitude, it's just a scalar. It's one value. If we want to fill that out so it's a time dimension or dimensioned along some other way, we can do that here as well. So this will return that data set. It's going to be filled with -9999 values or whatever is defined as missing value. And we can take NumPy and just generate some random data here, and we'll fill that into this temp mean variable. And as soon as this is done getting that object, we can see that nice printed data set, essentially. And like I said, that I want to say there's a lot of different versions of this MET. So I probably should have used a different DoD or a different instrument that had less, but this one is pretty standard and one of our most used data streams. But that should show up here, or I can let you just let it show up for you as well. It is interesting here that you can then write this out to netcdf. It would look exactly like an ARM file. If you clean it up and write it out like we talked about earlier, then it would be up to CF standards. So there's just a lot of different ways you could use this for those that want to submit data back to ARM. So with that, I'll actually, we got about 6 minutes left here. I'll leave it open for questions. I know there's been some questions and discussion in the chat. And Ken, I appreciate you and Geary here responding to them. But are there any other questions? Definitely get into the documentation, look all around at what's in there. Even in the discovery area, we can pull the ASOS data from the Iowa Mesonet. I know people are going to kind of look strangely at this, but you can actually get crop type information from a USDA Cropscape API, because that information is important to inform our measurements. When we're located out in a farmer's field and we're collecting surface flux data, that information is valuable. There's a lot of different IO modules to read in NOAA GML data. There's reading in NOAA PSL data, like their profiler that they have. Recently added in wrappers around Bobby's Pi SP2 to read in SP2. A lot of different types of plots here as well. I won't really dive into that. Again, Ken's done a fantastic job with the quality control area and getting tests in there. Here's actually that get solar azimuth elevation function. So we essentially could do that, get the information back, and plot it up pretty easily. So, and then the retrievals area as well. So, so yeah, there's a lot in there. I'm definitely surprised this still hasn't finished yet, but I guess, yeah, I'll leave it at that. If there's questions, feel free to chat or raise your hand. I hope this was helpful, at least in working with ARMS QC and maybe exploring some of the other areas of ACT. Definitely reach out on our issues page if you have feature requests or run into any problems. We also have a discussion area. Excuse me. Let me click all those off. So, if you want to add some new discussions, I've even put up some just show and tell type things. There's a category for that if you're using it and want to just show off what you've been doing. For instance, this is all of ARM's SWAT, which is our soil, water, and temperature system. It's an older system that been retired, but we plotted up read in all the data, plotted it up, and it used to be in multiple different kind of variable names, so it was kind of a lot to go through. But you know, we're definitely open to having more discussions on here as well. So, all right. Well, if there aren't any more questions, we can call it a day. So tomorrow there aren't any more talks. Let me pull up the agenda. So we'll be going over PyArt from noon Eastern for about an hour, and then Max is going to give about an hour-long tutorial on X-array and Pangeo, so diving more into X-array. And then we're going to close out at about 2 p.m. Eastern. We'll just meet and discuss, hopefully have an open discussion here, get a lot of good engagement on, you know, what do we see as next steps, and really close this workshop out. So, all right. Well, thanks everyone. I appreciate your time here. This has definitely been interesting for me, and I hope you all have been learning a lot as well. So, all right. Thanks everyone.